A few words of introduction. I would welcome comments on this subject. Contact details will appear later. Sadly, some of the artifacts no longer exist, so for images of them we rely on images made long ago. Some are not very good. Everyone is aware of the great achievements of Roman civil engineering. Although their wooden parts do not usually survive, large parts of many palaces, temples, baths, fortresses, roads, bridges, and aqueducts have survived very well, because they're made largely of stone, brick, tile, and concrete. They're very well known, and much is written about them, their architecture, and their construction. It seems that Roman mechanical engineering was also very impressive. Their machinery is said to have included cranes, derricks and shear legs, pile drivers and drop hammers, dredges, grain mills and olive presses, catapults and other machines of war, machines to cut stone, several different kinds of machine for raising water, and perhaps many other types of machine. But of all these machines, very little survives. Used on the surface, and using materials like wood, metal, rope, and leather, they became victims of recycling and decay. But there is one exception, the force pump. It is the only Roman machine of which we have remains of a substantial number of examples, and that's what I'm going to talk about. Some ancient texts about this machine survive, and I have taken them into account. But my work is based primarily on detailed examination of the remains and of the records made when they were found and afterwards. A number of force pumps did survive in the bottom of wells and elsewhere. The remains are substantial. From them we know their dimensions, how they were configured and driven, and what materials were used to make them. We know what the component parts were and how they were made and fixed together. We can recognize different models within an overall generic design, and we can estimate performance. So this exceptional machine gives us a unique insight into Roman mechanical engineering. All the known pumps are force pumps, not suction pumps. They raise water by pressurizing it and pushing it upwards. They do not suck it upwards. As in many very original ideas, the basic concept of the force pump appears simple. A cylinder is filled with water, a close-fitting piston is pushed into it. This forces the water out as a jet, or through a pipe to a higher level. The cylinder needs two valves, one at the inlet and one at the outlet. The concept is attributed to Ctesibius, who lived in Alexandria in about 270 BC. The force pump has three great advantages. It can pump water from a shaft that is both deep and narrow. It can pump water up a pipeline along an uneven, twisting incline, for example, from a sump in a mine. And, most important of all, it can produce a strong jet, for example, to fight fires. A pump could be used in a fixed installation to raise water from a well, or from a sump, a caisson, a cistern, or a stream, or as a portable pump, fixed in a tank of water which is carried on a cart, the tank being refilled with water from the nearest available source using buckets. Three ancient authors describe the force pump: Philo of Byzantium, Vitruvius, and Hero of Alexandria. All three say it's made from separate pieces of metal joined together, and Vitruvius and Hero say it's made of bronze. No ancient author mentions a design in wood. 10 pumps made of metal are now known. 6 of them are too small to be of much practical use. The bronze pump is made by soldering together many separate parts. This one has more than 30 parts. Using bronze has many disadvantages. Bronze is expensive. It needs a highly skilled worker. Each part must be cast and then filed to the exact shape required, and the parts must then be soldered together. It's difficult to take a bronze pump apart to maintain it or repair it, and to fix it in position by attaching it to anything else, and bronze may corrode if continually wet. At some point, perhaps in the 1st century AD, a pump was designed which works on the same basic principle, but is made of wood and in a completely different way. The spaces inside the machine and the passages which connect them are made by cutting holes into a single large block of oak. These holes are then secured against high water pressure by closing off their origins on the surface of the block with panels and plugs of wood. Thus, in the metal pump, the worker makes many individual parts and then joins them together to make a device which contains the spaces required. But in the wooden pump, he goes directly to making the spaces themselves. In comparison with metal pumps, wooden pumps use much cheaper materials, and they're much easier to manufacture, to assemble, to maintain and repair, and to fix in position, and their valves probably make better seals and leak less. Since wooden force pumps were cheaper and probably performed better than metal pumps, it's very likely that they became the dominant form of the water pump in the Roman world. So they are the principal focus of this talk. In general, unless the context indicates otherwise, I'll use pump to mean a Roman force pump made of wood. 18 Roman wooden pumps are known, and remains of 13 survive. They all have 2 cylinders, and they all follow the same generic design. 7 wooden force pumps have been found in ancient mines in Bulgaria, but it's now clear that they are not of Roman date, so I'll not include them in this talk. Ancient texts contain a number of references to pumps. Only one mentions using a pump to raise water from a well, and the text is debatable. None mentions using a pump to dewater a mine, but 10 mention the high jet that pumps produce, 7 mention pumps used to fight fires, and 3 mention the pumpers, or siphonarii, who worked them. Discussions with fire officers confirm that a pump of this type would be very useful in fighting a fire, and much more useful than throwing buckets of water at it. It seems likely that force pumps were used widely on the surface to fight fires, and it may be that they were also used on the surface to raise water to a tank at high level, from which it could flow to where it was needed. But there is a major problem. As far as we know, no wooden pumps used on the surface have survived. Our detailed knowledge of the wooden force pump therefore comes principally from study of examples which were used to pump water from wells and were preserved in them, and not from those used on the surface to fight fires or to raise water from ground level. This is the Bertrange pump at the bottom of its well, which is 5 meters deep. And here there is a depressed-looking Luxembourg archaeologist. Here and here are the pistons, and here is the pipe through which water is forced to the surface. This is the Bertrange pump in its operating position against the wall of the well. Here is the body of the pump. We call it the block. The pump has 2 cylinders. They are lined with lead tubes. Here are the flanges at the tops of the cylinders. Here are the 2 pistons in their cylinders. Here is the pipe. It is only partly visible. Struts support the pipe. Here is one of them. This map shows where the 18 known wooden pumps were found. All of them come from wells or sumps below ground level. Only one is known from Rome, but 3 were found in Milan and 2 in southern France, Lyon and Périgueux. 6 come from Trier, a major Roman city, and 4 more from sites nearby. 2 were found in southern England, at the Roman town of Silchester and at the villa at Tarrant Hinton in Dorset. But so far none are reported from Spain, Africa or the East. I'll discuss later why this might be after I've shown how the pump works. All the 18 known pumps come from a Roman context. We have dates for the 10 listed here. They are all AD. Of these 10, 2 are dated by dendrochronology to the 3rd century, 8 are dated by context in the range 2nd to 4th century. The other 8 pumps, not listed here, are not dated, but there's no indication that they are not also of this date range. In the early 1st century AD, the Emperor Augustus established the corps of vigiles, or watchmen. Fighting fires was an important part of their duties, and there is textual evidence that they had pumps to do this. Perhaps metal pumps were found to be expensive and unsatisfactory, and this created a demand for a cheap and effective substitute and led to the invention of the wooden pump. The Lyon pump shows the transition from bronze to wood. Its block is of wood, but its valves and cylinder liners are of bronze. Its wooden parts cannot be dated, but wood which may have formed part of the installation is dated to the late 1st century. This may indicate that the wooden pump was invented at that time. It is sometimes suggested that these pumps raise water by suction. If true, this would be a great advantage, because when raising water from a well, the pump could be located at ground level and not at the bottom of the well. However, it's clear that these pumps do not raise water by suction. They are force pumps. They are submerged in water and force it upwards by pressurizing it. There are a number of reasons for saying this. First, many pumps were found in their operating position at the bottom of a well. If they could suck water from wells up to ground level, it would be much more logical to install them on the surface. Second, to suck water up from a well, a suction pump on the surface would need long pipes attached to its bottom which run down into the water. But no suction pipes or attachments for them have been found. Third, to raise water by suction, a pump must create a partial vacuum. It's very unlikely that a wooden force pump could create the vacuum required. Fourth, for technical reasons, suction can lift water by only about 7 meters from the level of the water's surface. The level of water in the wells where pumps were found is not known and could vary greatly over time, but this limitation might have made it unviable to use suction pumps in them. A wooden pump includes wood which rots, leather which cracks, and iron which rusts, if they are often wet and then dry. This would happen to a suction pump on the surface. Submerging the block prevents this. I'll explain later how the machine functions internally to pump water and how its parts are made and assembled. But first, it must be very difficult to fix a pump at the bottom of a well. The wells are narrow and often deep. The block is buoyant and it's hard to submerge it in water. The parts are bulky and unwieldy, and the pump is subject to strong oscillating forces as each piston is pushed down in turn. So the block must be fixed very firmly. Usually the parts from the upper dry section of the well did not survive, but we do have this rather poor drawing made at the time of a pump found in 1922 installed in a well 8 meters deep. Here is the block of the pump at the bottom of the well. Here is the drive on the surface, and here is the pipeline between them. This is a close-up of the pump itself. It's held in place by planks wedged horizontally against the sides of the well. Here are the pistons. They project above the block. Here are wooden connecting rods. They connect the pistons to the drive on the surface. They're normally called conrods. Here is a guide plank. The conrods run through it to ensure they do not buckle. The pump is driven by a rocker arm on the surface. Here it is. The rocker has a central axle. It's inside the box here. The conrods are attached to the rocker here and here. As each side of the rocker moves down and then up, the conrods move the pistons down and up. The drawing is more or less plausible, but it shows the pump as being worked by only one person. It's likely that it was worked by two people and that the rocker extended to both sides of the axle, as I'll show in a moment. So how does the drive work? This diagram shows the drive in schematic form. Here is the rocker. Here is the axle on which it turns. Here are the pistons. Here are the conrods. Here are the joints where the conrods are connected to the rocker. They're called the big end joints. Here are the joints where the conrods are connected to the pistons. They are called the little end joints. At the moment shown in the diagram, the rocker has been swung to its fullest extent anti-clockwise. The left piston has been driven down to its bottom position. The right piston has been pulled up to its top position. The rocker will now be swung clockwise. The right piston will move down and the left piston will move up. No complete driving mechanism has yet been reported, but the iron fittings of a rocker, now corroded and misshapen, were found with the Bertrange pump. These are the remains of the rocker, seen from above. The rocker is made by fixing an iron strap to each side of a long wooden beam. The beam is 3 centimetres thick. The iron straps are held in place on the wooden beam by long iron rivets. The wooden beam has not survived. It would have been much longer than the straps. The straps provide metal bearings which form the axle and the other joints. Here are the straps. Here are rivets. This shows the straps from the side. The wooden conrods would be fixed firmly to hangers which swing from the 2 big ends. Here are the iron hangers. They should swing freely, but are now corroded in position. The drawing shows a reconstruction of a strap. There are 3 joints. Here is the central axle of the rocker. Here and here are the 2 big end joints. The 2 hangers swing from them. The conrods would be attached to the hangers. I'll show how the machine works internally to pump water, but first I'll explain its internal construction. Each of the 2 cylinders has an inlet valve and an outlet valve. These 4 valves direct how water flows through the pump. All of them are one-way valves. They let water pass upwards, but not downwards. I'll explain how an inlet valve works. The outlet valves work in the same way. Here, a little drum of wood is forced into the bottom of the cylinder. A hole has been bored through the drum so water can pass. The drum is held in place by friction. The valve is nailed to the top of the drum. It consists of a flap of leather stiffened with lead. I'll explain later how the valve is made. In this example, there is high pressure water below the valve and low pressure water above it. Water wants to flow from high pressure to low pressure, so the high pressure water pushes the flap upwards away from the drum. The passage through the valve is now open, so water can flow upwards. But in this example, there is high pressure water above the valve and low pressure water below it. Because water wants to flow from high pressure to low pressure, the high pressure water pushes the flap downwards onto the drum. This closes the passage through the drum and stops water flowing downwards. This image summarizes how the one-way valves control the flow of water. Water can flow upwards through them, but it cannot flow downwards through them. This diagram shows the internal arrangement of the pump. I'll describe each part and identify with a star the corresponding part on existing remains. The machine is symmetrical about its vertical central line, so I'll describe the parts in its centre and on its left side. This is the body of the pump, a block of oak. This is the valve chamber, cut into the front of the block. It would normally be closed by a panel of wood nailed across it and sealed with pitch. This is the block of the Benfeld pump. The cylinders are bored right through the block from top to bottom. This is the left cylinder liner, a tube of lead to give the cylinder a smooth lining. This is the left connecting passage. It carries water from the left cylinder to the valve chamber. This is the left piston. These are leather discs fixed to the end of the left piston. They form a tight seal between the piston and the liner to prevent water escaping past the piston. This is the outlet passage. It carries water from the valve chamber to the delivery pipe. This is the delivery pipe. It carries water to the surface. This is the connecting tube. It fits tightly into both the top of the block and the bottom of the pipe and makes a waterproof connection between them. This is the seat for the left inlet valve. This is the valve itself, fixed to the top of the seat. These are the two outlet valves in the valve chamber. They are made from a single flap of leather, as in this example from the Bertrange pump. This slide shows what happens inside the machine when it pumps water. The pump is submerged in the blue water of the well. Here and here, the brown parts are the two inlet valves. Here and here, the brown parts are the two outlet valves. All four valves are one way. They let water pass upwards, but not downwards. I'll use the word slug to mean the amount of water that fills a cylinder. The rocker is swinging clockwise. It's reached the horizontal, so it's halfway through a clockwise stroke. As it continues to move, this is what happens. On the right, the piston is coming down. It is putting pressure on the slug of water in the right cylinder and is forcing it out. This slug of water can't escape down into the well through the right inlet valve because this is a one-way valve and pushing it down from above makes it close. But this slug of water can escape up into the valve chamber through the right outlet valve because this also is a one-way valve and pushing it up from below makes it open. As this slug of water gets into the valve chamber, it can't escape down into the left cylinder through the left outlet valve because this is a one-way valve and pushing it down from above makes it close. So this slug of water is being forced up and into the lower part of the outlet passage. If the passage is full, this pushes a slug of water out of the top of the passage and into the lower part of the pipe. And if the pipe is full, this pushes a slug of water out of the top of the delivery pipe. On the left, the piston is going up. This reduces the pressure of the water at the bottom of the left cylinder. This allows water from the well to push open the left inlet valve from below and to flow into the left cylinder. This water can't escape past the left outlet valve because the high water pressure coming from the right side of the pump is keeping the left outlet valve closed. So this water is being forced into the left cylinder. It rests there, ready to be forced out when the rocker swings anti-clockwise on the next stroke. As pumping continues, a slug of water is pumped from each cylinder in turn, and a slug is pushed out of the top of the delivery pipe. Now we'll see an animation of the pump in action. First, slowly, it shows that as the pistons move, they change the pressure of the water in different parts of the pump, and the valves respond accordingly. So the pump takes in water from the well and forces it up the outlet pipe. And now, at what may be a realistic speed. We have some information about 12 of the wells in which pumps were found. The wells were circular and often narrow. It seems that their diameters ranged from 70 centimetres to 170 centimetres. 8 of the wells were over 6 metres deep. The Silchester pump was found in a well only 2.7 metres deep, but it seems likely that the pump was not in fact used there. At Tarrant Hinton, the well was 26.4 metres deep. If the pump found there was in fact used there, this means that it could withstand a water pressure of at least 2.5 bar. It seems that wooden pumps could probably raise water by at least 20 metres, so it may be that, when pumping water from a well, some raised water not just to the surface, but to a tank at high level from which it was fed by gravity to various parts of the site. For some of the 15 wells, the nature of the surrounding area suggests a particular use for the water. 6 for domestic use, 2 for making pottery, 1 for watering gardens or orchards, 1 for servicing baths. But for 5 wells, the nature of the surrounding area is not known. In 1908, a pump was found in the cellar of the amphitheatre at Trier. There are no remains, and we know little about it. But possible uses for it might include to dewater the cellar by pumping infiltrated water from a sump into the drain, or to fight fire in the wooden structures of the amphitheatre, or to spray perfume into the arena. In 1941, the Mentuccia pump was found in Rome at the bottom of a shaft, which may be one of those dug to enable the construction, underground, of the Aqua Appia, the first aqueduct of Rome. There are no remains, and it's not clear what the pump was used for. In 1995, the Martberg pump was found on the floor of a drying kiln in a hilltop sanctuary on the left bank of the Moselle, about 60 kilometres downstream from Trier. It was probably brought there from somewhere else on the site. There's no indication of where it came from or what it was used for. All the known wooden pumps follow the same generic design, but there are many differences in their layout and in their parts. Here are just a few examples. Usually, the 2 outlet valves are placed in a single valve chamber, as at Wederath on the left. But in 2 cases, each outlet valve is in a separate chamber, as at Oberkirch on the right. However, we have no reason to think that 2 separate chambers gives any particular advantage. Usually, the outlet valves are placed horizontally, as at Wederath and at Oberkirch, but in 2 other pumps, the connections are arranged so that the outlet valves hang vertically. This may make it easier for them to shed grit, which might otherwise stop the valves from closing properly. For 13 pumps, we know what the liners were made of. In 12, they are lead, as at Benfeld on the right, and as in the very decayed block from Riol on the left. At Lyon, The block is made of wood, not bronze, but nevertheless the flanges of its cylinders show that they are made of bronze, as can be seen here. So this pump has made part of the transition from bronze to wood, and this may indicate that it was one of the earliest wooden pumps. This is how the valves are usually made. A wooden pattern is made, shaped as seen on the left. A rod is pushed through its central hole. The pattern is pushed into a bed of sand and then removed. Molten lead is poured into the sand. It forms a lead plate with a stalk, as seen top right. Like the pattern, the plate has one straight edge. There are then 3 steps, as seen on the right, from top to bottom. 1. The plate is turned over so that the stalk points upwards. A flap of leather with a hole in its centre is placed over the stalk. Apparently goatskin is best. The flap is larger than the plate and projects beyond its straight edge. 2. The lead stalk is hammered down. It spreads out and clamps the flap to the plate. 3. The assembly is turned over and the projecting part of the flap is nailed to the wooden valve seat along its straight edge. The leather forms the hinge of the valve and also acts as a gasket. The valve opens by swinging upwards. Its seating stops it from swinging downwards. These are the valves from the Bertrand's pump. The water flows upwards through the valves in the following order. First, through the 2 inlet valves, seen here at the bottom of the image. The lead plates remain, but most of the leather is missing. Then, through the 2 outlet valves. They are made from a single piece of leather which was nailed along its central line in the wide valve chamber. And then, unusually, through an extra valve which was located in the delivery pipe to reduce the water pressure on the pump when it was not in use. The lead valve plates are of different shapes. Since each pump has at least 4 valves, the 18 known pumps would have had at least 72 valve plates. 42 have been recovered. Of these 42 plates, 21 are circular but have a straight edge, and 8 have 5 straight sides. But the remaining 13 plates are completely circular and have no straight edge. Perhaps their valves wobbled as they opened. In some pumps, all the valves were similar in shape and may have been made from the same pattern. If the leather flap failed, it would be easy to replace it. But in some pumps, the plates differ in shape. It may be that if a pump or its well failed, it might be possible to recover only some of its lead valve plates and to use them in a new pump. There are various ways of making the pistons. The body of the piston is a wooden rod. In many cases, the leather piston seals are attached to the rod by a long iron spike, which is driven into the head of the piston and held in place by friction. And to prevent the spike from splitting the piston, an iron sleeve is shrunk around its head. This is a piston from Périgueux. The seals are held to the piston head by an iron rod with a large head. The X-ray shows that the iron rod is held in place not by friction, but by a cotter pin. If the seals start to fail, it's easy to replace them by removing the cotter pin and withdrawing the iron rod. When designing a pump, there are 3 crucial dimensions to consider. The height through which water is to be raised, the lift. The distance through which each piston moves, the stroke. And the cross-sectional area of the lead liners, the liner area. These 3 dimensions, together with the speed at which the pump is driven, the cycle speed, determine 3 critical things: the output of the pump, and the force and the power required to drive it. The performance of the pump will also be affected by the power lost through friction and the water lost through leakage. The relationship between the various parameters is complex. I don't suggest that Roman makers knew how these parameters arise or how to calculate their effects, but probably rules of thumb emerged from practical experience and were used to determine the dimensions to be used in any particular case. How was the power provided? Driving a pump requires reciprocating motion in a vertical plane, and the motion must be closely controlled to prevent the pistons overrunning. Animals can produce usable power by walking in a horizontal circle, but reproducing reciprocating, vertical, controlled motion from this would be very difficult. I conclude that pumps were driven by human operators. If a pump was to be used to raise water from a well, the maker would need to take into account the lift required and the size of the crew which would drive the pump. For example, suppose the pump would normally be driven by a crew of 2. If the well is deep, the force required to drive a pump with wide cylinders might be too great for 2 operators. If so, it could be reduced by narrowing the cylinders. This would reduce the output of the pump, but output could be increased by having a long stroke. We might therefore expect the cylinders and lead liners of pumps used in wells to be long and narrow. It is likely that a portable pump used on the surface to fight fires is kept submerged in a tank which is carried on a cart. The cart is rushed to the fire, and as the pump is worked, the tank is kept filled with water from the nearest available source using buckets. Bystanders would join the sifonarii, forming a big crew which would drive the pump as fast as possible with great force and power. To enable a big crew to work the rocker, it would have to be rather long. To prevent the ends of the rocker swinging too high and out of reach, the stroke would have to be rather short. But output could be increased by having wide cylinders. We might therefore expect the cylinders and lead liners of pumps used to fight fires to be short and wide. Now let's see how these various considerations apply in practice. We have the required information for 15 of the 18 known wooden pumps. This diagram shows their 2 crucial dimensions. On the vertical axis, the stroke. On the horizontal axis, the liner area. For many of these pumps, their dimensions are fairly similar. They are shown as blue dots, but 4, shown as red dots, are outliers. Tarrant Hinton, top left, TH, and Vederath, far left, WE, were found in the deepest wells. They had to provide a very high lift. They have small liner areas. This is consistent with reducing the force required to drive a pump, providing a very high lift. And, as expected, to compensate for this, they have very long strokes. Silchester, top right, SI, has a very long stroke. This would indicate use in a deep well, but it was found in a well only 2.7 metres deep. This is a major reason for suggesting that it was not used in that well. Lyon, bottom right, LY, has the shortest stroke and the largest area. This might mean that it was a fire pump, but it was found in a well with its bronze liners intact, so it was probably used in that well. I conclude that the diagram does not show that these 15 pumps are of 2 separate classes corresponding to fixed and portable use. The output of a wooden force pump depends on the dimensions of the pump, what it's asked to do, and how it's driven. I've made calculations for what I call a representative pump of typical dimensions doing a typical job. This is shown as the red dot RP in the centre of the diagram. For the purpose of calculation, I've assumed that The liners have an internal diameter of 70 millimetres. The stroke is 250 millimetres. The pump raises water 10 metres. 10% of the power input to the pump is absorbed by friction and turbulence, and 20% of the swept volume of the cylinders is lost through leakage. Here are the results. Suppose the rocker is driven at 20 cycles per minute, so there are 40 strokes per minute. Then the pump delivers 31 litres per minute and requires a power input of 71 watts. If we assume that an operator working a rocker can produce, say, 50 watts, then one operator could not drive the pump at this speed, but two could do so fairly easily. As noted earlier, no wooden pumps are known from the outer areas of Spain, Africa, or the East. A number of reasons for this may be considered. Was the necessary know-how available there? It seems likely that it was. 2 metal force pumps were found in mines in Spain, and 2 wooden force pumps were found in Britain. So the technology did travel to distant areas. Were the necessary materials available? Lead was widely available. The key item was the block of oak, but presumably other wood could be used if oak was not available. The diameter of the trunk required is probably about 50 centimetres. It seems unlikely that trunks of this size were available only in the West. But in any event, this size is needed for a pump which has 2 cylinders in a single block. A pump with only 1 cylinder could be made from a much narrower trunk. It could be operated on its own, or perhaps combined with another 1-cylinder pump to form a 2-cylinder pump. So it seems that materials were probably available. Were there suitable wells? If there is a lot of sand or gravel in a well, the stream of pressurized water will abrade the internal spaces of a wooden pump. But it seems unlikely that in the outer areas most wells were unsuitable for this reason. Were there pumps in wells but they left no trace? This also seems unlikely. If an installation failed, it would be attractive to remove its lead liners, but one could climb down into the well and remove them without removing the block. This was probably done at Perikika and may have been done at Vederath. The wooden block would remain in the well, and as its fixings failed, it would fall to the bottom. If this was continually damp, the block might survive, and even if all the wood, iron and leather disappeared, the 4 lead valve plates would survive. Perhaps the outer areas were too dry for blocks in wells to be preserved there. But even if the liners were removed and the wooden parts perished, the 4 lead valve plates would survive. On balance, it seems unlikely that the apparently uneven distribution of pumps in wells is due to poor preservation in dry areas. Could it be a problem of excavation, recognition and reporting? Were remains missed during excavation, as perhaps at Silchester, or found but not recognised, as at San Giovanni in Milan, or recognised but not reported, as with the Riol pump in Trier? Well, perhaps. Finally, a pump is more valuable in areas where the water table is low, so that raising water from wells by bucket is more onerous, and in areas where labour is less readily available, so that labour saving is attractive. But it's difficult to know how these considerations actually affected the distribution of pumps in wells. I conclude that at present we cannot identify any particular reason why wooden pumps have been reported in wells in the West, but not in Spain, Africa, or the East. But in any event, 18 wooden pumps is a small number of finds from the very large number of wells which have been excavated. This may indicate that wooden pumps were not used very often in wells anywhere in the empire, and that the uneven distribution of finds is due mostly to chance. If many wooden pumps were used at ground level, but few were used in wells, the fundamental reasons for this disparity probably lie in performance and economics. As regards performance, if a pump is used to raise water from a well to provide an ongoing water supply, it may be worked very hard. If it's used for, say, 6 hours a day, 365 days a year, at 15 cycles per minute, the leather seals and valve flaps will each move about 4 million times per year. They may fail fairly frequently under such heavy use. If they do, it's very burdensome to repair them, as they are submerged at the bottom of the well. In contrast, a portable pump at ground level may be worked much less often, and if it fails, it's comparatively easy to repair. As regards economics, it may be that the more efficient use of labour, obtained by raising water from a well by pumping rather than by using a bucket, did not justify the cost of making, installing, maintaining and repairing a pump in it. In contrast, a portable pump on the surface which can fight fires would be very valuable. It may be that wooden pumps were used quite commonly on the surface to raise water from cisterns and streams and to fight fires, and in this talk I've tried to show how Roman mechanical engineers transformed the Greek metal force pump into a much better and cheaper machine by changing radically how it was made and the materials used to make it, and then continued to make changes to the new design in the search for yet further improvements. But our present knowledge of Roman pumping technology comes not from pumps on the surface, but from pumps which were used at the bottom of wells. So it may be that the present archaeological record is providing evidence for only a small part of Rome's use of the wooden pressure vessel. We know from texts and from some remains and images that the force pump was only one of many different types of machine used in the Roman world for many different purposes. But we know very little about their design, how they were made, what they were made of, how they worked, and, crucially, what they could do. New technology can change society, and as Roman mechanical engineers were able to produce a machine as useful and as ingenious as the wooden force pump, it seems likely that many of the other machines they produced were also very useful and very ingenious, and that Roman mechanical engineering made a valuable contribution to the Roman world. How unfortunate that our knowledge in detail of this contribution is limited to that of the wooden force pump. I'm going to end with a puzzle. This is the back of the Bertrange pump. Here, XV, the Roman 15, is scratched across the grain. This suggests that pumps like this may have been numerous. But what does 15 mean? This pump is size 15, or model number 15, or the 15th of the batch ordered by the town council, or the 15th I've made this year? I'd welcome suggestions, and thank you for watching this presentation.